Data is the lifeblood of any machine learning project. Well, just as a chef needs fresh, high-quality ingredients to cook a delicious meal, a data scientist needs clean, well-prepared data to build an accurate and reliable model. Think of your raw dataset as a collection of uncooked ingredients. Some might be perfect, some a little bruised, some missing altogether. The process of cleaning these ingredients is called data preprocessing. It is the very first and arguably the most important step in our journey. It ensures our model does not fail because of simple errors or inconsistencies, setting a solid foundation for everything that follows. Once our data is clean, we can move on to feature engineering. We combine and transform basic ingredients to create stronger signals. We might create a new feature from existing ones to capture patterns. This step blends domain knowledge, creativity, and analytical skill. Good features can make a simple model shine, while poor ones hurt even complex algorithms. We will walk through pre-processing and feature engineering using the famous Titanic dataset and Python. It is small, yet realistic, with missing values, categorical text, and hidden patterns. We will use simple language, clear code, and explain not just what we do, but why it matters. Data preparation is not a chore. It is a thoughtful process that dramatically improves results. Our journey begins with loading the data into our workspace. We use Pandas, the standard tool for data manipulation. The data is stored in a CSV file. Pandas reads it into a data frame, a neat table. We start with pd.read.csv to load the Titanic data. This single line turns a static file into a dynamic object. The first step is simple, yet fundamental. Once loaded into DF, we get a feel for what it contains. We do not dive into cleaning before understanding the landscape. We use df head to see the first 5 rows. It shows columns like P-class, name, sex, age, and survived. A quick sanity check. df.info gives rows, non-null counts, and data types, integer, float, object. Our first real clue, missing data in columns like age and cabin. For numerics, df describe shows count, mean, std, min, quartiles, and max. We inspect distributions and spot outliers, especially in fair. This exploration builds intuition and helps plan pre-processing. Next, we handle missing values with care. After our initial investigation, we have a clear list of suspects, columns with missing values. Missing data can cause errors and bias our analysis if not handled properly. Our first target is the age column. Dropping rows loses information. A better approach is imputation. For numerics, the median is simple and robust. df age, filner, df age, median, in place, true. Embarked sometimes has a few missing values. For categoricals, use the mode, the most frequent value. df embarked. Filner, df embarked. Mode, sent in place data true. Now the column is complete without inventing a new category. Cabin is missing for a large majority. Filling with one value adds noise. Option 1, drop it. df.drop, cabin, axis doctor 1, in place, true. Option 2, extract the first letter, dec, and fill missing with U to salvage signal. The choice depends on problem and experimentation. For this lesson, we will drop it to keep focus clear. But remember, you have options. Discarding a noisy, sparse feature can prevent the model from learning randomness. Dropping features is an essential part of cleaning. With missing values handled, we can create powerful new features. With our data clean, we move from cleaning to creating. Names hide valuable titles like Mr., Mrs., Miss, Master, df, title, scuct df, name, .sestra.extract, azaza plus, expand false. We inspect unique values, then group rare titles into a single rare category to reduce cardinality. This simplification helps models generalize better. SIBSP and Parch alone may be weak, but together they reveal family size. df, family size. df, SIBSP, plus df, Parch, plus 1, This can capture dynamics of large families versus solo travelers. Is alone, so 1, if family size, so 1, else 0. Simple binary flags are interpretable and often very effective. Next, we translate categorical text into numbers with encoding. Our models are mathematical. They understand numbers, not words. So we convert categorical features into a numerical format. For binary categories like sex, map one value to 0 and the other to 1. A simple label encoding. For multi-class features like embarked, label encoding implies false order. Use one hot encoding instead. Each category becomes its own 0-1 column. Pandas makes it easy with pd.getDummies, drop first true, to avoid multi-collinearity. After encoding, drop original text columns to keep only numerics. We now have original numeric features, engineered features, and new binary one-hots. The data is fully translated into the language of mathematics. The importance of feature scaling. Age ranges Hazasu 80, while fair can exceed 500. Differing scales can bias some models. Distance-driven models and those using gradient descent, like SVMs, logistic regression, and neural nets, are scale-sensitive. Standardization sets mean to 0 and std to 1 using scikit-learn's standard scaler. Apply it to wide-range numerics like age and fair. Binary one-hot columns do not need scaling. Values typically fall within a few standard deviations of 0. Tree-based models like decision trees and random forests are not scale-sensitive. Still, scaling is a best practice for many pipelines and ensures each feature contributes fairly. An introduction to feature selection. After cleaning and engineering, we may have many columns. Are all useful? Less can be more. Irrelevant or redundant features can confuse models and slow training. Computer correlation matrix and review correlations with survived. Near zero correlations may be candidates to drop. Train a random forest to get feature importances based on impurity reduction. Plot importances to rank features. Often title, sex, and p-class rank highly. You might keep the top set and remove others. Iterate. Train with all features, then a reduced set and compare performance. Aim for the smallest feature set that delivers strong predictive power. We have arrived at the final step before training, splitting our data. Evaluating on the same data can be misleading. Models can memorize training data. Set aside a test set to act as stand-in for new, unseen data. A common split is 80% for training and 20% for testing. Separate X and Y, X for inputs, Y for the target. X train, X test, Y train, Y test, I train, test. Split. X, Y, test, size 0.2, random state 42. Always split before scaling. Fit the scaler on X to train only. Then use that fitted scaler to transform X to train and X to test. This prevents information leaking from test into training. By mirroring real-world constraints, we build trustworthy models. Your clean data awaits its destiny. We cleaned, transformed, and enriched the Titanic dataset. We began by loading and exploring the data, then handled missing values carefully. We engineered informative features, encoded categoricals to numeric form, scaled key numeric features, selected meaningful features, and split data for honest evaluation. We now have X to train, X test, Y to train, and Y test model ready. Next, train models like logistic regression, random forest, and gradient boosting with cross-validation. The time you invest in preparation is never wasted. Keep practicing, keep experimenting. A clean dataset is your greatest asset in machine learning.